Put 7 animals in the same living room, and the room does not stay the same. The red ball on the rug almost disappears. The flower on the table grows a hidden bullseye. A mouse behind the couch turns into a warm ghost. The aquarium in the corner starts flashing secret signals that you cannot see at all. Nothing moved. Nothing was painted. The only thing that changed was the animal looking at it. Imagine this room clearly. A green rug, a red rubber ball, a blue blanket on a gray couch, a yellow lamp, a white flower in a pot by the window, a warm mug on the table, a mouse tucked in the shadow near the wall. Outside the window, a fence, a tree, and the sky. In the corner, a saltwater aquarium with coral and a mantis shrimp hiding under a rock. To you, this is ordinary. To 7 animals, it is 7 different worlds. Start with a dog at the doorway. A dog does not enter a black and white room. That old idea is wrong. The dog sees color, but it is a smaller color world than yours. Human eyes usually build color from 3 kinds of cone cells. Dogs have 2 main kinds. Their world is strongest around blues and yellows, while reds and greens are much harder to separate. So the blue blanket on the couch still has power. The yellow lampshade still stands out. But the red ball on the green rug has lost its trick. To you, red against green is loud. To the dog, those 2 colors can slide towards similar muddy tones. The ball is not invisible because shape, brightness, smell, and motion still matter, but it no longer screams red. This is why the dog may run straight past a red toy lying still in grass, then snap to it the moment it moves. The room is not organized by your color labels. It is organized by contrast, motion, edges, and scent. The dog is not living in a duller version of your world. It is living in a different priority system. Now the lights go low, and the cat steps in. The cat does not win by seeing every color. The cat wins by collecting light that you waste. In dim rooms, human vision gets grainy fast. The cat's eyes are built for dusk, corners, and the thin stripe of light under a door. More of its retina is packed for low-light sensitivity, and behind the retina sits a reflective layer called the tapetum lucidum. That mirror-like layer gives incoming light a second chance to hit the light-sensitive cells. It is the reason a cat's eyes can flare in headlights or a flashlight. In our room, the couch is no longer just a dark lump. The gap under it opens up. The mouse's tiny movement at the wall becomes the most important event in the room. But this night advantage has a trade. The cat's picture is not a perfect high-definition movie. Extra sensitivity can come with softer detail, and the cat's color world is more limited than ours. The red ball does not matter much. The twitch does. The shadow does. The small moving body near the baseboard becomes the center of reality. For the cat, the room is not darker. It is more huntable. Now shrink the viewer down to the size of a bee and fly toward the flower on the table. This may be the strangest change in the whole room, because the flower has been hiding a sign from you. Many flowers reflect ultraviolet patterns that human eyes cannot detect. Bees can see ultraviolet, along with blue and green. They do not see red the way you do, but they gain an invisible layer that turns some petals into landing maps. That plain white flower may no longer be plain. Its petals can show darker ultraviolet zones near the center, like arrows painted toward the nectar. What looked decorative to you becomes instructional to a bee. The flower is not just pretty, it is giving directions. This is a beautiful bargain between plant and insect. The bee needs food, the flower needs pollen carried away. So the plant advertises in a visual language that many humans walk past without noticing. The bee does not need to understand the whole room. It does not care about the couch, the television, or the framed photo on the wall. It cares about the target. To the bee, the room is a landscape of bright signals and dead zones. The flower is not sitting quietly on the table. It is broadcasting. Now slide down to the floor and bring in a pit viper. This animal changes the room in a way that feels like science fiction because it is not only using its eyes. Pit vipers have heat-sensing pits on the face, between the eyes and nostrils. These pits detect infrared radiation, the heat energy coming off warm objects. The snake is not seeing heat with an eyeball like ours. It is sensing heat with a specialized organ, then using that information with vision. In our room, the red ball is just an object. The blue blanket is just fabric. The wall is cool. The table is cool. But the mug leaves a warm patch. The dog's body glows. The mouse behind the couch becomes a small, living source of heat against a cooler background. That is the key. The snake is not admiring a rainbow thermal poster. It is solving a hunting problem. A warm-blooded animal can hide in darkness. It can freeze in place. It can blend into leaves or shadows, but it still leaks heat. For the pit viper, the most important object in the room may be the thing you cannot see at all. A mouse tucked behind the couch is visually hidden from you, almost silent to the dog, and barely a flicker to the cat if it holds still. To the snake, it is a warm shape in the wrong place. The room has become a temperature map. Now make the room bigger because a horse is about to walk through it. A horse's eyes sit on the sides of its head, and that changes the entire geometry of the world. You look mostly forward. A horse sees a huge sweep around its body. It has a broad panoramic field with a smaller zone in front where both eyes overlap. That is excellent if you are an animal that survives by noticing danger before danger reaches you. In our room, the horse does not have to stare straight at the window to know something moved near it. The side of the room matters. The space behind and beside the body matters. The world wraps around. But there are blind spots built into this design. Very close in front of the face can disappear. Directly behind the horse can also vanish. That is why a horse may lower, raise, or turn its head to inspect something that seems obvious to you. It is not being dramatic. It is moving the object into a better part of its visual field. The horse also does not see color exactly as humans do. Like the dog, it has a more limited color system, while motion and contrast remain crucial. So the room is not a painting first, it is a safety scan first. For the horse, the question is not, what color is the ball? The question is, did anything change at the edge of the world? Now leave the room entirely and look through the window from the top of a tree. The eagle is watching. An eagle does not need the room to be close. Its visual system is built for distance and detail. Raptors have extremely sharp vision, with specialized regions of the retina that give them high-resolution sight. While you may see a general living room through the window, the eagle can lock onto fine contrast and tiny movements from far away. The mouse near the wall is no longer just a possibility, it is a precise target. A twitching whisker, a shift of fur against the floor, the small shape crossing from shadow to light. Those details matter because a hunting bird cannot afford a vague world. It must turn distance into information. But sharper does not mean magical. The eagle is not reading your book from a mile away or seeing through walls. Its power is resolution, focus, and motion detection at distances that would make our eyes give up. In our room, the stitching on the blanket, the edge of the ball, and the mouse's body outline all become cleaner. The eagle's version of the room has less mystery in the faraway parts. Distance has been pulled closer. Finally, look into the aquarium. The mantis shrimp lives in a world so visually strange that people often describe it badly. It does not simply see a prettier rainbow than humans. Its eyes are stranger than that. They sit on stalks, move independently, and contain specialized bands of photoreceptors that can detect many wavelengths, including ultraviolet. Many mantis shrimp can also detect polarized light, which is light whose waves are oriented in particular directions. To us, the aquarium is coral, rock, sand, glare, and moving water. To a mantis shrimp, parts of that same scene can carry extra channels of information. Reflections off bodies, shells, and the water itself may contain polarization patterns. Some mantis shrimp use polarized signals in social displays, creating a kind of private visual message hidden inside the light. So the aquarium is not just colorful, it is coded. A rival mantis shrimp near a burrow may not just look bright, it may be flashing information in a channel many animals cannot read. A transparent or shiny prey animal may not blend the same way. Glare may not be just glare, it may have structure. This is the deepest twist in the room. Human vision feels complete because it is the only version we have ever owned. But the mantis shrimp reminds us that light contains more than our brains report. Ultraviolet is real, polarization is real, infrared radiation is real. We are not seeing the room as it is. We are seeing the slice of the room our eyes evolved to use. And that is what all 7 animals reveal. The dog turns color into a blue-yellow puzzle where the famous red ball loses its power. The cat turns darkness into hunting space. The bee finds a secret target painted on a flower. The pit viper finds the warm body hidden behind furniture. The horse stretches the room sideways into a danger scanner. The eagle drags tiny details out of distance. The mantis shrimp opens a coded world inside water and light. Same couch, same rug, same flower, same mouse, same aquarium. 7 animals walk into one ordinary room, and none of them enter the same place.